Yeah, so thanks, Avi. So this is talk about private optimization and some connections with statistical physics. And the problem that leads to these connections is this problem that is studied in theoretical computer science and elsewhere in machine learning, the problem of low rank matrix approximation. So the plan of this talk will be that first I'm going to introduce this low rank matrix approximation problem, then talk a little bit about private algorithm, the notion of privacy and utility for these problems, and then give two algorithms for two different types of privacies. And the connections to physics or statistical physics would be that the first algorithm I'm going to present will actually also resolve some problems in physics, some in particular, some people who have, I think Harish Chandra was here, right? At that point, yeah. So, and then the second part of this talk will be about using some results from statistical physics, in particular results of Freeman-Dyson on Dyson-Brownian motion to analyze the utility of certain algorithms. So this is a summary. Everything will be explained. Please feel free to interrupt and ask questions as and when you would like. So what's a high-level problem? So the high-level problem is the following. You're given some data matrix. The data consists of data of users. So the rows are users, and then there are some features. So one thing that we would be interested in the covariance matrix of this data. So the matrix is M cross D, but the covariance matrix is D cross D. It lives in the space of features. And I think throughout this talk, I will use this notation that sigma 1 to sigma D are the non-negative eigenvalues of this covariance matrix.
We think of K of M larger than D or smaller?
M is larger than
larger.
Yeah. And the goal is to output some low rank approximation to M, where low is quantified by an input parameter K, but the notion of approximation is not unique, and we will look at some different notions of approximations. There's also this notation that I will use. So these small sigmas are the eigenvalues of M. If you write this diagonal matrix, capital sigma with the eigenvalues sigma 1 to sigma D, and V to be a set of orthonormal eigenvectors of M, then we can look at this diagonalization of M as well. So it's a standard notation. So here are some variations, both in terms of what it means to approximate and how it means to approximate. So one can consider a more general problem where you are given some target eigenvalues, lambda 1 to lambda D. Okay. And what I would like is to find a matrix with these target eigenvalues, lambda 1 to lambda D, which is as close to the given matrix. And the closeness can be measured in two different ways, many more ways, but two different ways. One is in terms of measuring the inner product between the given matrix and the space of all matrices with eigenvalues lambda 1 to lambda D. Okay. F here just denotes the Frobenius inner product between these matrices. And the other is the distance, Frobenius distance. So one you would like to maximize because the inner product you would want to be as close to it as possible. And the distance we want to minimize.
It's more general because for row n, you take the last eigenvalue.
Right, so I'm gonna, right. So what are the special cases? And these are the two main cases which are important in practice. One is that we want to approximate the given covariance matrix by just any rank K matrix. Okay, So here it turns out that the optimal choice for lambda is just sigma I is for the top k eigenvalues and zeros for the rest. And there is a related problem where the goal is to output the best subspace that approximates this matrix. Here, we let lambda 1 to lambda k to be 1 and the rest lambdas to be 0. But pretty much everything I will say in this talk will be applicable to the general lambda case, although I think if you were to pick one problem, this is a good application to keep in mind. So classically, there's not really anything that has not been said about this problem. We know the optimal solution for this in both these norms. And the optimal solution is that the set of orthonormal vectors or this matrix, the unitary matrix that you're going to pick, would just be the set of orthonormal eigenvectors of V. And that gives rise to the following approximation here, that you look at this diagonalization, but this sigma, which is the diagonal consisting of all sigma 1, sigma 2 to sigma d, you just chop it off after k and let them all be 0. It's still a D cross D matrix. Okay, it's not a rank, it's a rank K matrix, but it is still a D cross D rank K matrix. Okay, any questions about the setup? Okay. So this has many applications in, I mean, almost all domains. Data arises in many, many domains. And the problem of outputting this low rank approximation arises as a way to reduce dimensionality in data. It's also this, you might have heard of PCA, the principal component analysis. The simplest interesting case of this problem, I mean, if you want to think about it, is when you want to just output the largest eigenvector of this matrix. So that corresponds to k equal to 1. Okay, so this is all classical stuff. I mean, a very basic problem appears in many different areas. The kind of more recent twist on this problem is that this matrix M, because it is derived from some data matrix, may contain sensitive information about the users which participated in this data, and we need algorithms which are able to preserve some privacy of these individuals. I haven't mentioned what privacy is, and I'm going to tell you in the next slides. But the goal is not just to make it private, because I can always make anything private by just not even looking at this matrix and outputting something random, just a random rank A matrix. But that is presumably not very useful, because we still would like to be able to output something which can be used for further computations or further reductions if these things are being used. So privacy is a bit more complicated to define, and I will do that. But let me say what notion of usefulness we may consider, given that we already have these things. So corresponding to this Frobenius inner product measure, one notion of utility or usefulness is the difference between the inner products. So we know that the optimal solution is V. So this is what we should be outputting. But maybe we'll output something else, because we can't really output V anymore. So we'll output some V hat. Okay. So one measure of difference is to look at so one measure of utility is to look at the difference between the inner products, between what we output and what we should output. Similarly, for this Frobenius norm distance, the notion of utility is to look at what we should have output versus what we output. And while the optimal solution is the same for pretty much any notion of distance you take in the traditional version of the problem. When we will have some constraint of being private, these things will not be the same. This is important to note. And there's a lot of nuance that arises because we are changing how we measure approximations and utilities. Completely different techniques might sometimes be required to analyze and find the optimal choices for the VHATs. So we're going to see some of that. So why is why can't we just release the data? I mean, or anonymize or something like that. So this is not at all my work. This is well-known stuff by now. And the motivation for understanding privacy or formalizing privacy. First of all, one of the earlier approaches to privacy was to release anonymized data. This doesn't work because even moderately dimensional data about people tends to be unique, pretty unique. And from that, one can determine who the person is. Even if I remove the name. I mean, Avi is so unique that even if I remove Avi's name from any table and I give out, various features, let's say, different types of awards or number of papers or number of postdocs, he will be clearly identified. So anonymization doesn't really work, okay, for many applications. Covariances are also can be unsafe, and yeah, so this is something that people thought, okay, we are not really releasing raw data, but maybe if you release covariance matrices, that could be okay. But there are simple examples which show that this is not necessarily enough as well. And I guess one of the reasons is that if there are just a few people in each group, and then one can kind of reverse engineer from the correlations about which genetic profiles are present and which genetic profiles are not present. Okay, so this is not a talk about this. I'm just giving you these pointers if you want to think about it. If not, that's perfectly fine. So about more than a decade ago, the question became increasingly pressing about how to compute these things privately, usefully, and also efficiently. So these are the three constraints that we have: privacy, utility, and efficiency. So in 2006, Dwork, McSherry, Nissim, and Smith came up with this notion of differential privacy, which is a notion of stability of an algorithm. And roughly speaking, it says that the participation of a single individual does not change the outcome by much. So in some sense, because the input consists of data from users, and if I take one user and swap it out with the data of another user, then the outcome of this, the algorithm, for it to be private, should not change much. Now, what does it mean outcome should not change much? Well, first of all, they argued that you can't have any deterministic protocol which will achieve this. So the output must be a probability distribution, even though the original problem was outputting, it's a solution to some optimization problem. The privatized version of it should correspond to outputting a probability distribution over solution space, which is a sampling algorithm. So it's some going from optimization to sample. And in particular, they gave a very precise definition of,
Just to start sampling, I mean, you add noise.
well, we will come to how to add noise.
Yeah, no, I'm not talking about how, but the source of privacy.
Not necessarily. I mean, so yeah, that's what I said. So if you have a domain, let's say, and you're optimizing over that domain, so the optimal solution could be this point, right? What you might say is that since I don't want to output always the optimal solution, I want to spread this probability distribution out. So you can view that as noise as well. But in physics, actually, before optimization took over, this was the notion. I mean, we never thought of nature optimizing functions in a sense. I mean, this whole theory of Gibbs distribution, there was an energy functional, and then the state in which a system was the probability of being in a certain state was proportional to its energy in some way.
No, the only reason I mention it is because all the privacy literature calls it noise and you call it sampling. So I wanted to make sure that these are
So
the same.
So the reason why I'm working on this
It's
is,
just a name.
right, it's just a name. I mean, noise, I think, was prohibiting me from working on this, but the moment I realized that there are non-trivial sampling problems, which is an area which I worked on, then I got a bit more interested in this. So leaving my personal opinions and reasons apart, so the definition involved two parameters, an epsilon and a delta. They have different roles to play. So you can think of e to the epsilon as just 1 plus epsilon. There are some reasons why they talk about e to the epsilon. But for a moment, if you think of delta being 0, then all this is saying is that the two probability distributions on one input versus another input, where the data sets just differ on one person, the densities are pointwise within 1 plus epsilon. Pointwise. So it's a very strong notion of closeness of two density, much stronger than TV or KL and so on. Okay? So this is called pure differential privacy. And this has many advantages. Ideally, you would like this. But as you can imagine, well, we can do this in some cases, and I will give you an algorithm to do this. Sometimes it's also it does slow you down either in terms of the number of users that you need before these bounds are meaningful or running times. And so they also have the forethought and define an additive error in probability. Okay, so now delta doesn't depend on the scale, it is just some additive. So this is the notion of privacy that we will talk about. I'm not going to give any proofs about differential privacy of any protocol. Some of them are actually just pretty straightforward. So I can maybe give you a hint in a second, but yeah, so any questions about the notion of privacy for those of you who have not seen it? Okay, so our task is the following, right? So if I look for pure differential privacy, we were looking for some low rank matrix which optimizes some function, right? So a natural thing would be to consider the Gibbs density corresponding to that function that we are trying to optimize and sample from that. This is the absolute most natural thing you should do, and that is what is called the exponential mechanism in this literature on differential privacy. It says, so I'm just stating it in our setting of low rank approximations and not the most general setting, but this is the same idea. So remember, our task was to maximize the inner product between the given matrix M and this X, where X was ranging over the space of low rank matrices. D cross D, but low rank matrices. So because I wanted to maximize it what I do is reduce the task of designing epsilon differentially private or pure epsilon pure differentially private algorithm to this sampling problem, which says, can you sample a matrix X from this density, this log linear density on this measure with respect to this measure mu. So that is the goal. Epsilon is essentially needed here, but it's just a constant, so it doesn't really play any fundamental, it doesn't pose any difficulty this way or that way in designing an algorithm. Yes.
Can I just clarify the goals event? Is the goal to get like a fast runtime or like
the goal is to get
what are the targets?
Any efficient algorithm is fine.
Efficient is like polynomial.
Yeah, polynomial time. Yeah. So this is so that's why I said, I mean, the proof said that if you can sample from this density, then the resulting matrix X will be epsilon differentially private. This, how to sample from this was not known actually.
So just to clarify another point, while extremely natural, the choice of Gibbs measure is, there can be other distributions that pick places
Right.
which are from a different distribution, but they satisfy the inequality of privacy.
Well, there are also entropy maximizing distributions.
So you can imagine,
Yeah.
yeah. So, but this is just natural.
That's right. This is the most natural thing. It works, but you can also think of other things that. Yeah. So the point to note, and I think that's what Avi's saying, is that the peak of this density is at the right point. Okay. But that's also not really necessary, but that's a property that this has. And yeah, so this is what I was saying. In statistical physics, 100 years ago, people were not thinking of optimization. I mean, there is no optimal state in many physical settings. It was just a distribution. But sampling, as we started discovering computational complexity of sampling, it turned out to be harder than optimization. So one thing I may not have mentioned or forgot to mention, that finding the optimal solution to the original low rank problem is just eigenvector, eigenvalue computation. So that can be done in polynomial time, at least up to some bit precision and so on. Okay. It's not trivial, but it can be done. But this raises the problem of sampling from the space, some space of low rank matrices. So let's understand what this space of matrices is. So actually these class of matrices have a name. In mathematics, they are called unitary orbits, because what we're looking at is conjugation by unitary operators of a given lambda diagonal matrix. So in particular, all matrices in this orbit of lambda, orbit because there's a group action by conjugation. So the unitary group acts on lambda by conjugation. And you can check that, you can apply unitary again to it and you will still get a unitary, because the product of two unitary matrices is a unitary matrix. So you get an orbit, okay? This is not a convex set in any ways, for any value of k. But I mean, the nice thing is that you can still do probability on this set. This is not always true. But in this case, it is true because this orbit, you can push forward the Haar measure on the unitary group to this orbit. And that's what this mu is. Okay, we also need to be able to do probability on this one. And I guess the most interesting or one special case of this is with something that you already know. This is the space of all rank K projection matrices, which is just the Grassmannian. Okay, and the rank 1 projection matrices is just a complex unit sphere. So the basic problem is to sample from a log linear density on a complex unit sphere. This problem was open. There are many heuristics, but there was no efficient algorithm known for it. So that's a problem that we are going to talk about. Okay, and we can look at it more generally. We can forget all the motivation if you don't care about it and just focus on this. That there are two matrices. One defines the orbit, the other defines the objective. Y defines the objective, lambda defines the orbit, and you would like to sample. So when I started thinking about this, actually I realized that, I mean, there is a certain amount of symmetry between lambda and y here. It's not really, yeah, you may also consider the problem where the orbit corresponds to y and the objective function corresponds to lambda. And indeed, such densities had been considered by Harishchandra, who was a mathematician, and he was trying to develop a theory of Lie groups, and two physicists, Itzikson and Zuber, who were using these densities on the unitary group as models of various things like quantum gravity and so on. So if you, I can just give a talk on this density. It has so many applications. And when something is so fundamental, there has to be some reasons for it as well. And there are good reasons why this quantity is so fundamental. So the results that were known, and when I started looking at it, it's called the Harishchandra-Itzikson-Zuber formula. It's a formula for the integral of this density over the unitary group. So in particular, what Harishchandra was able to do actually for even more general Lie groups, even before Itzikson and Zuber, and Itzikson and Zuber, I think, rediscovered that formula for the unitary group, that they could write down this integral as a determinant. So you may ask, what is the connection between the determinant and the unitary group? I mean, this is an integral over the unitary group. The determinant is a summation, which is also a discrete integral over the symmetric group. Anybody knows this here? I'm just curious.
I've seen a lecture of yours.
Yeah. So the connection is that the group UD, the unitary group, is related to the symmetric group because of work of Yale. When he was trying to classify Lie groups, he showed that every such compact Lie group has an associated discrete group which has all the information about this continuous group. So in particular, the integral can be reduced to the symmetric group on the elements. That was very surprising because this could end up being anything, but it ends up being a determinant. What was missing is how to compute, how to sample given the ability to compute partition function. So in computer science, we know, through results of various people, including Leslie Valiant, Mark Jerome, and others. Probably I'm missing some names, I'm not sure. But that if you want to compute the partition function, for example, if you want to count the number of perfect matchings in a bipartite graph, it is sufficient to sample. There is a self-reducibility problem. Here, the work on computing the partition function is already done. But what was not clear is how to use that to sample. So anyways, so what is the connection? Well, these are the same problems actually. I mean, and this is not very hard to see through a simple map which maps a unitary matrix to a matrix in the orbit of lambda. By this mapping, you can move back and forth across these two problems.
Replacing the trace by the inner product by the trace.
No, not just that. I mean, this U lambda U star we call X.
Yeah.
Yeah. Yeah, and the trace by the inner product. Yeah. Yeah, that's right. So these are the same problems. If you find an efficient algorithm for this problem, you will find an efficient algorithm for sampling from these densities and vice versa. So that's the question. Okay, so this is a result obtained with Jonathan Leake and Colin McSwiggan, which is a polynomial time algorithm to sample from these density matrices, from these log linear densities over these orbits. Okay. So you can parse the running. I mean, it has some dependencies on the norms of the input matrices. It can be independent. And it has many applications actually beyond this differential primacy. Interestingly, the reason why I came up to this problem in a different way was to try to understand actually the following quantum inference problem, which is, suppose I give you a density matrix, and I would like you to represent this density matrix as a probability distribution or rank one projection matrices. What is a way to do it? So von Neumann suggested one way to do it, which is to just pick any orthonormal basis and write it. What we looked at was another way, which is the maximum entropy basis, which now you have a distribution which is supported over every projection matrix. So when you try to figure this out, this problem of quantum inference, you end up coming to this problem exactly. So we needed this algorithm for other purposes as well. Okay, so this is the result. Any questions? So there was some prior work by Kapralov and Talwar for k equal to 1. It's a very complex algorithm. Not quite sure about the correctness, but I'll give you a very simple and elegant proof idea as to how to do this. So first, let me recall how do you sample from a random unitary matrix? How do you get a random unitary matrix? You pick a random Gaussian vector, then you orthogonalize everything with respect to it and repeat. So this is easy. Okay. So this corresponds to the this corresponds to the kind of the just sampling from the base measure, I mean, just the uniform density on the base measure. The problem when this matrix is not zero is that this term here is not unitarily invariant. And the entries of this matrix X derived from this orbit can get very correlated. In fact, this is an algebraic variety as well in this orbit. So it's a very high degree variety in some sense, and the correlations are hard to disentangle. So one idea is to view the matrix X in this orbit in terms of eigenvalues. But then you'd say, don't all matrices X in this space of orbit, in this space of orbit of lambda have the same eigenvalues? The answer is yes. What about eigenvalues of all leading minors? So what does that mean? Let me explain to you. So this is the matrix X. This lives in that orbit. So if I look at the eigenvalues of the entire matrix, this is just lambda 1, lambda 2, lambda 3. There are three, it's a 3 cross 3 matrix here. But if I look at these eigenvalues of this 2 cross 2 leading principal minor, I get another 2 eigenvalues. If I look at this, then I get another eigenvalue. So you can imagine doing this for a D cross D matrix. So you're going to get D plus D minus 1 plus D minus 2 all the way till 1.
Explain why 1.
Why I want to, yeah. Why am I looking at it? That's I'm going to explain that. This is yeah. So here is a nice exercise actually. If you give me the eigenvalues of all leading principal minors of X, then I can essentially determine the eigenvectors of this matrix.
If you know the eigenvalues, can't you also determine the eigenvector?
No, because I mean, in this, if I just know the eigenvalues, which are just lambda 1 to lambda n, I mean, I don't have no idea what the eigenvectors of X are.
Okay, you don't know X.
I don't know X, yeah.
Okay, yeah.
Yeah. So it's a decoding problem. I will just give you these numbers.
Yeah.
Okay. And from this, I'm able to recover the magnitude of eigenvectors. It's a little bit more to it than you can't recover the entire matrix from this. But this is a very good. So this mapping has been studied. It has a name. It's called the Rayleigh map, which maps a matrix X to a set of numbers. And what is nice about this mapping, this MathCal R or the Rayleigh map, is that there are additional inequalities that these numbers satisfy, which are through standard this Cauchy interlacing theorems, which I guess people here know, that this number lies between this number and this number. This number lies between this number and this number. In fact, this is why it's written in this funny manner. It's actually a triangle. And what is known is that these interlacing inequalities, along with these inequalities mentioned here with this boundary condition, is a polytope. So we had this non-convex object or an orbit O lambda. When we take the image of this map, it gives rise to a polytope, and this has a name. It's called the Gelfand-Chaitin polytope. Okay, so polytope is fine. When we ask, there's a measure here. What happens to the measure? And if you do this kind of mapping with, we tried different mappings. I must say, this is not the first mapping that we tried. This particular mapping projects the uniform measure of this orbit to a uniform measure on this polytope. So that wasn't true for things like standard moment polytopes, where we know that it's not just uniform, it breaks up into some polynomials over some Voronoi regions and so on. So that was very complicated and messy. This was, I think, the first time we felt that there might be some hope here. This idea that things under group action when mapped by some reasonable thing gives rise to polytopes has been, in Avi's work, this has been very central actually, and this is known for a very long time. But I think how measures map not very well studied, I would say. And something even more is true, that if I now look at this log linear density on this orbit, and I look at the push forward map of this density, I get an exponential density on a polytope. Okay? So this puts the problem squarely in the domain of theoretical computer science, where we have spent decades developing how to sample from log concave densities on polytopes. There's no easier way to do this than invoking general theorems about log concave sampling on polytopes. Let me just say that. So the algorithm now is very simple. First, you sample a point R in the GT polytope of lambda with respect to the exponential density. This is something we do using results of the, developed by Kannan, Loash, Fries, and Jerome, and so many other people. So that you can use that line of work. And subsequently, we need to sample from the fiber, which is we need to take this point back. But these proofs are not holding by some kind of, some thread. These are very robust proofs, and these proofs actually tell us how to go back. And this lemma or this exercise I mentioned, how to go back from the eigenvalues to the eigenvectors, is essentially playing out a role here. So that's it. You have to believe me that these things can be done. And yeah, so the rank one case, this corresponds to this. Actually, the GT polytope for the rank one case is just a simplex. So for k equal to 1, it's just a probability simplex. And it's actually not trivial to sample from a log linear density on a simplex. At least I don't know of a direct way to do this. Yeah.
Just to clarify the algorithm one more time, like, are you just sampling over this exponential distribution on the Gelfand whatever polytope?
Yes.
And then given those eigenvalues, you just like recover, let's say, a uniformly random matrix that
Correct. Right.
map
So
over, like,
for this, I'm writing very straightforwardly what the mapping is.
Okay. Yeah, sure.
So for this, I'm just telling you for the k equal to 1 case, I can explicitly write down what the inverse map is. So which is yeah, so the V is the thing that you sample from the simplex, and then you sample additional complex signs, quote unquote, and then you output this Z1 times square root of V1 and so on.
This is the description of the fiber.
That's a description of the fiber in the rank one case. Yeah. Yeah, so I mean, if you were to change this exponential density into something different, all of this stuff will not work. So it's yeah. Okay, so this was the first result. Hopefully you learned something interesting. I mean, for me, the most interesting take home from here was that you can sample from these non-convex objects if you realize that these objects are not just non-convex, they have some symmetries. And these symmetries play a very crucial role in this reduction. So I would just view this as a reduction from this non-convex to the convex case. Yes.
So like you said that the eigenvalues uniquely determine the eigenvectors. So the fiber is just given by the complex signs.
Almost determines, yeah. It doesn't uniquely determine.
But like up to the complex sign.
Yeah, up to
So the fiber is given by these complex signs.
kind of, yeah. There is still a little bit to it than what I'm saying, but yeah. You can look at the paper and you'll see the precise thing. And actually, I think Terry Cow has a whole discussion, which is a substantial paper on what you can do from eigenvalues, and he traces the whole history. And apparently, there's it's a big area. But I think the reason why he says he wrote it is because it was not known. And so, if you're interested in these inverse problems, I would recommend you look at his notes, which is probably available from his website. Okay, let's move on to another way to construct private mechanisms. Okay, so one way to view what we did was that we had this optimal solution. So there's an input space of the matrix, and then there is a output space of rank K projection matrices or rank K matrices. Okay. So in this approach that I suggested, told you before, quote unquote, we added noise in the output space, right? But one can just also consider adding noise in the input space. And that's what was suggested in a paper of Cynthia Dwork, Kunal Talwar, Thakurta, and Zhang. But here, for whatever reason, you can't really get epsilon zero privacy, you get epsilon delta differential privacy. So what was the algorithm that they suggested? Just add Gaussian noise to this matrix. So remember that the matrix M is symmetric positive semi-definite. So you add some Gaussian noise, and the variance of this noise essentially, which is root T, is determined by the privacy parameters. You don't have to understand that. If you ever work on this problem, you can look at the proof of this, not difficult, but that's not the point. The point is that you compute this perturbation first, then you diagonalize this perturbation, and then just output the optimal solution for this diagonalization. So this is called the Gaussian mechanism. Okay. And they prove some results on this, basically using matrix perturbation results like Davis-Kahan theorems. If you know what they are, Avi probably knows what they are. These are worst case perturbation bounds. If I have a matrix and I perturb it, then how much can the eigenvalues change? So somehow they were not leveraging the fact that this is not a worst case perturbation, but a Gaussian perturbation. So we started thinking about that. How can you leverage it? And it naturally takes you into this area of random matrix theory, where even if this matrix is just a zero matrix, it's already an interesting problem. In fact, that is the basic case in random matrix theory. You have these entries are Gaussian. So this is called I think this is called the Gaussian orthogonal ensemble, GOE. And you want to understand the distribution of eigenvalues of this. So this was work. Yeah, I'm not good at history of these things, but I mean, this was started by Wigner, I guess. Wigner, right? Yeah.
So who understand hydrogen.
Right. But Freeman Dyson actually came up with a proof of the this what is called this Guinevere formula for the distribution of eigenvalues of GOE or GUE or the symplectic case by viewing the addition of the Gaussian noise as a matrix valued Brownian motion. So I'll explain this, and I think that's what I will do. I'm not sure I have time to go into the proof of this. So this idea, I mean, I kind of already told you the punchline here. So that's what we observed in a paper in 2022 with Oren Mangubi. And that just kind of changed the whole paradigm of analysis of this. What Dyson did was incredible, in my opinion. I mean, he observed that once you view this as a Brownian motion, I mean, adding a Gaussian noise of a certain variance, you can also think of adding it incrementally. It gives you a stochastic path where the matrix M is going slowly from M to M hat. So its eigenvalues are also changing. Its eigenvectors are also changing. I mean, who would imagine that you can write down equations for evolution of these eigenvalues and eigenvectors, and Dyson did that. He wrote down stochastic differential equations for the evolution of that. And that, as it is useful to improve prior works under some strong assumptions. So, which is what we did in this 2022 paper, where we suggested that one should view the Gaussian mechanism through the lens of Freeman-Dyson. But these assumptions were strong, and we wanted to get rid of them and genuinely improve prior work. So, and this will become clear in a second, in a couple of minutes, probably not in a second. So in this, this year we published a paper where we suggested a variant of this Gaussian mechanism, which adds complex Gaussian noise. Okay, and I will explain to you why this seemingly trivial thing of going from real Gaussian to complex Gaussian, at least we don't know how to make it work with the real Gaussian. But the nice thing about differential privacy of these things is that they satisfy some property called post-processing. So you may compute a complex matrix, but then you can just convert this complex matrix into a real matrix in some standard way, and this will not violate the differential privacy property. So it's actually okay to do that. You can even move to quaternions if you like, if complexes are not enough. And we could do that.
You don't violate the privacy if you measure it using this Frobenius distance.
No.
That's,
Yeah. Well, frobenius distance is the utility. That's not to do with privacy. So the utility will depend on the Gaussian. But the privacy is the hard constraint. Yeah. Yeah, privacy is the hard constraint. Yeah, utility will go by some constant factor because essentially you're increasing the dimension by a factor of 2. So this is the main result, which says that you can get a Frobenius distance bound, which is something like root k times root d. T is just a constant. It depends on epsilon and delta. And then there is this term here, which in some sense has to be there because if you're trying to do a rank K approximation of a matrix, there has to be some gap in the K and K plus first eigenvalues. Otherwise, it doesn't make any sense. So this improves upon the previous bounds by a factor of root K. So before the bounds were K times root D and so on. And we can also get similar results for other problems that I introduced, such as subspace recovery.
The improvement is in the utility.
Yeah, improvement is in the utility, yes, but by a different mechanism. Right. Yeah, we want to improve the utility. But it goes down because, by some constant factor 2 in some sense, but that kind of disappears. And the main technical lemma, besides using all this stochastic differential equations and stochastic calculus, is a new result on the distribution of eigenvalue gaps. So if you consider this process, stochastic process, where you're slowly or adding Gaussian, complex Gaussian matrix, and you look at the eigenvalues at time t, then these eigenvalues can't come close, very close. And I'll tell you in the next slide why understanding the closeness of these eigenvalues is crucial. Okay, it's not at all clear what the relation of this to this is. And the relation will become clear once we start talking about. But yeah, this result is an independent result which is of interest in random matrix theory. Yeah.
Well, what is for m equals 0? What is now? This is GOA and stuff.
Well, even for m equal to 0, no, but even for m equal to 0, this is this was not known.
So the eigenvalue gaps for GOA are known.
But not with this probability bound. So this S square was known. So we needed SQ, we need a better bound than S square.
Yeah.
So that's a little bit of an improvement. Yeah. Okay, so let me show you the equations actually, which I think is the most interesting thing, which if you have not seen before. So this idea of adding, so we are back to the real case for the moment. The Gaussian case. So one thing you could do is track the eigenvalues and eigenvectors, and these are equations that Dyson wrote down for how the eigenvalues evolve as a function of time and how the eigenvectors evolve as a function of time. And this is not a standard differential equation. This is a stochastic differential equation. This is the Brownian motion term. This is like the pure noise. And this is some drift term. I want you to focus, and I think this may be the main take home from this part of the talk, is if you have not seen this before, is what does this term do? What this term does is that if two eigenvalues start coming close to each other, right? Then there's repulsion. This is the same idea, by the way, which is inherent in all of these spectrosparsifiers. So, you know what I'm talking about probably. I don't want to give secret messages. Even Spielman-Srivastava, yeah. It's this idea of repulsion, which is inherent, is because of, essentially it's a rank one. The way Dyson computes this is by doing a rank one instantaneous Taylor approximation, except you can't really do Taylor approximation because it's a stochastic trajectory, so you use Ito calculus and stuff like that.
But it's basically the Sherman-Morris.
That's correct. It is basically
rank one of the
correct.
formula.
That's correct.
Yeah.
So what happens is that if you start with a matrix which is all zero eigenvalues, right? They can never cross each other if you're able to track each eigenvalues. And there is a whole, I mean, there are so many beautiful stochastic processes which are equivalent to this and so on that people have developed based on this understanding. So this way of viewing random matrices has been very powerful, and in particular has been used in these universality laws for random matrices, if you know what they are. Similarly, he also wrote down how the eigenvector evolves. It has a similar equation. Any questions? So what is the approach of using Dyson-Brownian motion to bound the utility? This is the approach from our previous paper last year. Let me just show you all the steps and then it's actually pretty straightforward once you realize that there are equations. So what we do is we define this process on the orbit. So as the matrix is changing in this matrix space, it gives rise to a certain stochastic path on the orbit. And phi t is the point on the orbit. Okay? And the orbit is fixed here. Lambda is fixed. Okay? Lambdas are the target eigenvalues. I want to go to sigma 1 to sigma k. The top k eigenvalues of the input matrix. The orbit is not changing, and then one can write down the stochastic path that this point in the orbit is taking using Dyson's equations, because it is completely determined by the eigenvalues and eigenvectors. So if I know how these are changing, I can write it down, and then we can integrate. I mean, we want to compute the distance between, what is this is essentially the utility measure. This can be written using fundamental calculus as integral over the path. The problem is these denominators. If we can somehow argue that eigenvalue gaps remain large throughout the time of running this stochastic process, then these terms will not blow up, and we can bound them and get the improvements. Okay, so in the previous work, we just essentially enforce this by saying that if we assume already that the starting eigenvalue gaps of the matrix are large, then because we run it for a certain amount of time, they still cannot come so close by these worst case. So here we indeed end up using some worst case spectral node bounds. Okay. And then this was a paper in Europe, so we checked for various practical data, real world data matrices. This assumption actually was true, that the top k eigenvalues, all of them have large gaps. But that's fine. So, this is the proof strategy. This will take time if you want to do this. It's something like that even I learned. I never studied stochastic differential equations before. Yeah.
I must be missing something. If the original matrix is 0, then the eigenvalues are not separated at the start, right?
Yeah, but this only applies to the separated case.
I see. Okay.
Yeah. So the results currently do not apply for the zero matrix case. But so what Avi was saying is that the gap probabilities between eigenvalues of random matrices have been very well studied for the zero case.
Yeah.
Okay.
Yeah.
We need it not just for the zero case, but for the general case.
Okay. Yeah.
So there our proof first gives a new coupling argument which reduces the general problem to the zero case. In some sense, it is sufficient to prove for the zero case. And even for the zero case, we couldn't find bounds which were good enough, so we had to prove those bounds. So the core argument is for the zero case, for these eigenvalue gaps. Okay, so I think I'll just show you this slide. and then I will conclude. So what does the complex Gaussian, so there are two new ideas actually in this newer paper. One is why fix the orbit? Before, remember what we were doing, we had this input matrix M, there was a target orbit where we want to land. And so we are moving this matrix here slowly and just observing the trajectory on the target orbit. Now what we are doing is we are changing the target orbit as well. Okay, this is a slick trick because we are not fixing the orbit. In the end, the target orbit will be the desired orbit. Sorry, in the end, the orbit will be the target orbit. So we will be looking at the right quantity, but somehow by doing this, certain cancellations happen.
So the orbit you look at is the orbit with the current eigenvalue.
Correct. That's correct. Yeah, that makes sense. Yeah. So that was one step. That doesn't require any complex part. The complex part was needed to get stronger bounds. What is known about Dyson-Brownian motion for the complex case in general, you can, so before I had put in beta equal to, I think, 1 or half, something like this, but this beta gets larger than the real case by a factor of 2 when you consider complex Brownian motion. There is more repulsion actually. So if you look at these curves, so these are eigenvalues of the real Gaussian starting from 0. These are eigenvalues of the complex Gaussian. So you get larger room to work with. And that turns out to be enough for us to prove this. Okay? The proof is not difficult, but it requires some ideas, in particular from mean field theory results, some people I think at various times have been affiliated to IES. But you can consider some kind of curves which are deterministic and then argue that these eigenvalues are just kind of oscillating around these curves. So this is the mean field theory approach to understanding. I think Erdős has one of the best results on this topic. So anyway, so this is how roughly it looks like. I can talk to you more. I'm around after lunch. If you want to know details about the proof, but hopefully you got some interesting ideas to take home, even though you may not be interested in necessarily in this problem. And that was, I mean, in some sense, I think the key take homes are that there are these really interesting connections between optimization and statistical physics. Both problems at private optimization and statistical physics are about sampling, or what is the right way to add noise. And we saw two completely different approaches to private optimization. One is while looking at densities and orbits and coming up with fast algorithms or efficient algorithms to sample from such densities. And then here, the algorithm is very easy to implement. You just add noise and compute eigenvectors. But the analysis uses ideas from the work of Freeman-Dyson. And I think the core results of this paper should be useful in problems where you want to understand, you're given a matrix and you want to understand what happens to its eigenvalues when you perturb it. So if you have ever used things like Davis-Kahan theorems, you should look at the main result of this paper, which may allow you to get better bounds by using the fact that the perturbation is not worst case, but random. So that's a result of independent interest for computer scientists. And for people interested in random matrix theory, we get these new gap bounds. Yeah, it's not clear to me to what extent the complex noise is necessary, but yeah, currently it is. So I'll conclude. Thank you so much for your attention.
Questions?
do physicists ever like add noise first and then kind of measure the partition function that way?
I don't know.
Okay.
Yes.
I guess it's your second work connected to the
Yeah,
statistical physics
well,
also, or-
I think generally in the anybody who's working with data in the real world will not assume that data is what it is. I mean, data always has some noise. When you make a measurement, there will be some intrinsic noise in most processes. So I think this is a reasonable thing to assume. Yeah, but I don't know. Yeah, a lot of different types of physicists, so I don't know who thinks what.
More question. So what, in general, when you in the two solutions you showed us, one you perturb the output and one you perturb the input. You could
Yeah.
do either
You could do either.
and fix the privacy.
Yeah,
What will give you a better?
I don't know the answer.
You don't know.
No. I mean, what is the best way to add noise? I don't
No,
know.
but you already suggested two ways of adding
Yeah,
noise.
yeah,
For a particular privacy limit, epsilon delta, you one perturb the output in some way and it's something from the
well,
output.
both perturb the output.
Well, eventually, yes.
Yeah.
But one directly and one via perturbing the. And you can, well, you get bounds of the utility in each case. Which bound is better?
Well, there are different utilities, first of all, and different notions of privacy also.
You use the same Frobenius distance.
No, it was one was a Frobenius inner product.
You did, one was this,
Yeah.
because one cannot be analyzed in either.
Right.
So each
Right.
method
You
is
can't
good for
do
one.
Gibbs of e to the minus.
Yeah, well, so I guess.
Yeah, so there's a lot of trickery.
Yeah.
And also, yeah, the nice thing about the first approach was that it gave you pure differential privacy. This adding Gaussian noise cannot give you pure differential privacy. You'll have to add noise of very large variance. Yeah, but I think that maybe one can try an even third approach, which is to add noise on the Grassmannian. The problem with that is that the Grassmannian doesn't have any geometry as such, other than its own intrinsic geometry. So somehow the geometry should be associated to the input matrix M, and it is not clear how to do that directly on this. Yeah, I mean, there are results, I think, in mathematics which show that Dyson Brownian motion is actually a Brownian motion on some manifold with respect to some geometry. It's like pure, I mean, as if you're doing Brownian motion on this manifold with respect to some Riemannian geometry. But yeah, I think finding the optimal geometry is something that I don't know.
It's very little, it's 13 months old.
More questions?
It's
Thanks.
Thank you.